Friends, here what we want to do is that we have x and some values of the variable x. We want another variable y and we want to generate equal number of values under y as in x such that when we calculate the correlation coefficient between x and y, that correlation is certain predetermined value like say 0.72 or it may be something like 0.85 or minus 0.47 or 0.05. What we want to do is the reverse of what we generally do. Generally we have x and y and we calculate the correlation. Here we have x values. We are given a fixed correlation coefficient and we want to generate the values of y. So friends, let us try this. We are in R and we are writing commands in R. We are first generating a random sample of size 50 from a normal distribution with a mean of 3.8 and standard deviation 2.1. What we intend to do is that we want another random sample of same size, but that particular random sample should have a correlation of 0.76. Say 0.76 with that of x1. A formula for that purpose is given by this. So this is the formula for that. That means known values of x1 are placed one after another in the following formula. R represents the correlation coefficient which we want, which you desire to have, and multiplied by another random set of random numbers of same size with the same standard deviation as that of x1. And mean may be anything else. So here we generate, if you look at this command in R, so you see the standard deviation of both the sets are same. So that is the trick here. So in order to generate correlated random numbers, we need to have the same standard deviation from both the data sets. Obviously the sample size should remain the same. And now if we want to check out that really if x1 and x2 have the same correlation coefficient, in R we have this particular formula to calculate the correlation coefficient. Now let us go back to R and check out whether this works nicely or not. So friends, as promised, we are in R console now. So we had already, as you can see here, we had already generated 15 random numbers from normal distribution with mean 3.8 and standard deviation 2.1. And then we have declared the correlation coefficient as well, 0.76. It is up to your wish, whatever you want. You may take any other desired value within the range, obviously from -1 to +1. Now this is the formula that we had talked about, and as you can see we have the same sample size, same standard deviation but a different mean. Now we press the enter button, and then once we press the enter we come down here. If you want to check out that whether really x2 is something like x2 is generated, you can check it out here. So these are the random samples that we have generated. And now we are interested to calculate the correlation between x1 and x2. So here we get, we write in, don't mix up with the case because R is case sensitive. So it's in capital letters. So x1 and x2 is in capital letters. And now you see it's 0.76 was the desired correlation. And we have here 0.79. So it is close to the correlation that we have desired. If we increase the sample size further, say if you take it to 20, 30, 50, you will find that the correlation is coming closer to 0.76. So this is what we have in R. So here let us try a variant of the example that we had done earlier. In earlier case we had a normal distribution from where we took the random sample, but in this case we have some fixed numbers. These numbers might have been generated from some example or some experiment where we have actually 25 subjects and we have measured their weight, and these measurements we are storing as a variable in R with the same name, weight. And so this is the command for taking the data to R under a variable, and then we are declaring the correlation coefficient which we desire. For simplicity we have kept it same as that of the previous value, 0.76, and then this is the formula. The formula is same that of the previous one. Here you can see we are using a normal distribution, generating random numbers from a normal distribution with the same number of observation as in the weight variable, and then this mean you can take any value of the mean, but the standard deviation has to be same as that of the previous variable. So that is the trick to get the correlated or random numbers, because the standard deviation of the two data sets needs to be the same. And then we can want to see what are the values stored under height through this command. We can write this and check it in R. And then we want to check the correlation coefficient definitely, because we have done an experiment, we want to find the result of that experiment. And as you know, the correlation of height and weight should be very close to 0.76. So let us try this in R and see if it really works. So we are in R now. So we had written the command. This first command we have taken the values of the variable named it as weight. In the second command we have defined the correlation coefficient, our desired correlation coefficient. And third line we have written the formula with the help of which we will be generating the value of height, which is expected to be related to weight with the correlation coefficient 0.76. So here we do. Now if we want to check what is the value of height or what values are stored in height, so we write this and then we get this. These are the values which we have come across under weight, under height, and then we calculate the correlation coefficient and write and calculate. So you see the value comes out to be 0.8239, not so much close to 0.76, but then there will be some amount of difference. As we keep on increasing our sample size, it might work well. If you are not satisfied, then we may once again try it like this, that we once again do this because this is a random number, so it will give you a different set of values, and then we try the correlation and check out. Yes, this time you see the correlation is coming up to be very close. So if you are not satisfied at one go, you may repeat it, and then you will get, after 2 or 3 attempts, you will get a better or closer correlation coefficient which is desired. We try another variant here. In this case, we may want the generated variable, the new variable that is generated, which is a fixed correlation coefficient with the first variable, should be in a particular range. So let us take this example. We want the height data correlated to weight with a fixed correlation coefficient, but we want the value of the new variable, that is the height variable, to lie between 120 and 180. So if we want to do this, what we will do here, we will do what is called as normalization, and we will use this formula. Height variable, we will calculate the minimum height using this in R and maximum height using this in R, and then using this formula we will convert the height data, those 25 values, within the range of 0 to 1. So the new variables will be saved in Z as values lying between 0 to 1. The maximum one will have a value of 1 and the minimum one will have a value 0. And now for converting those values to the new set of values lying between 120 and 180, here we take 120 and plus the range of these will come up here. So 180 minus 120, so that is 60 multiplied by the value of Z. So this will actually convert the height of the individuals within a new range of 120 to 180. And if you want to check it out that whether these values are perfect, then we can click on height new and see the new values of height, and then if we calculate the new values of height and weight, correlation coefficient we'll see that it is close to our desired correlation value that we want. So we are in R once again now. So the first command, as you can see at the top, is the normalized command. This is used for normalizing the height data set within the range of 0 to 1, and this is the transformation which takes it within the range of 120 to 180. That is what we actually discussed earlier. And then we write this command to calculate the correlation coefficient, and then as we press enter, we find that the correlation coefficient comes out to be very close to 0.76, which we wanted. So this is how we make the transformation of the data set within a particular range. Last but not the least, one thing which is not generally shown in other tutorials, that we have calculated, we have got the values, but how we can get the value out of R. So these two commands will help you to get the value out of R written down in an Excel file, so that you can use it for further analysis in any other type of software. So this is, we are making a data frame of the variables. One is the height data, which has been converted into 120 to 180 and called it height new. That is the name of the variable, and the weight data. And we save it as a data frame in DF. DF is the name of a data frame. This is optional, you can give some other name. Not optional, you have to give some name. But any name, you may give it data, data1, you may write your name, whatever. But this part, this command to be the data.frame. And then this data frame is written as a CSV file, and this is the name of the file, height underscore weight.csv. And then we press enter. This does not bring any command or anything like that, any indication that the file has been created, etc. But the interesting thing is that when you escape to My Documents or Documents folder, you will find that a file is created by that name. And when you click on this file, okay, so you will end up in the Excel file like this. So this will write the height and the weight and the values and serial number. So you can see the 25 values here. If you want to check the correlation coefficient in that Excel, this will not be written, but just I want to continue. So this is the CORREL, that is the command of calculating correlation coefficient in Excel. So from the first value we come to the last one, and then we give a comma, and then we click and drag from the next value of the variable to the last one, and then when you press enter, we get the correlation coefficient, and you see it's 0.74, the same as that which is generated by R. Thank you for watching this video. Please subscribe our channel Statisticians Hub and give a like to this particular video. Thanks for watching.